Good morning, children. Today we will see about the stereochemical aspect of nucleophilic substitution reaction. In order to understand the stereochemical aspect of substitution reaction, we need to learn some basic stereochemical principles and polarization. Now we will see about the terms, that is optical activity, seriality, retention, inversion and racemization. Now let us see about the optical activity. A plane polarized light produced by passing ordinary light through a Nichols prism is rotated when it is passed through the solution of certain compounds. Such compounds which can rotate the plane polarized light are called as optically active compounds. The angle by which the plane polarized light is rotated is measured by an instrument called polarimeter. If the compounds rotate the plane of the polarized light towards the right side or clockwise direction, then it is called as the dextro-rotatory, and it was represented by D form and is indicated by a symbol positive. Before the degree of rotation, if the light is rotated towards the left, that is anti-clockwise direction, the compound is said to be levorotatory or L form and indicated by negative sign. Such compounds which have positive or negative optical rotations are called as optical isomers, and the phenomenon is called as optical isomerism. Now let us see about the molecular symmetry, asymmetry, seriality and enantiomers. Suppose if you cut a paper and if you can fold it exactly, and then the area where you can fold it exactly and to make two equal halves, that is what we call as a plane of symmetry. Now certain compounds exist in the form of mirror images led by the foundation of modern stereochemistry. He determined that aqueous solution of both the type of crystals shows optical rotations equal to the magnitude for solutions of equal concentration but opposite in directions. He believed that, Louis Pasteur believed that this difference in the optical activity was associated with the three-dimensional configurations of the atom in the molecules, that is, configuration of two types of crystals. J. Van Hoff and C. Lee Belt in the same year, that is in 1874, independently assigned that the arrangement of four groups, that is valency, around the central carbon atom is tetrahedral if all the substituents attached to the carbon atoms are different, then the mirror images of the molecule is not superimposable. Superimposable means is not overlap on the molecules. Such a carbon is called as asymmetric carbons or stereocenter. So you need to understand that a stereocenter is the center where the image and the original particles does not overlap directly. This stereocenters resulting the molecule would be lack of symmetry, and such a molecule is called as asymmetric molecules. The asymmetry of the molecules along with the non-superimposability of the mirror images is responsible for the optical activity in organic compound. So you need to understand that an optical activity of a compound is based on non-superimposable mirror images. That means due to the seriality. This term is called as a seriality. That means if a carbon having 4 different valencies, means the 4 different groups which are satisfied to the valency, that gives asymmetric carbon. So asymmetry of the carbon is the properties which we require for the optical activity of a compound. Now let us see, the symmetry and asymmetry are also observed in many days to days. Object, a sphere, a cube, a cone are all identical to their mirror images. For example, your left hand and right hand look similar, but if you put your left hand on the right hand by moving them in the same plane, they does not coincide. That means they does not overlap directly. The object which are non-superimposable on their mirror images, non-superimposable on their mirror images are said to be serial, and this property is called as a seriality. So the term serial means object which have non-superimposable on their mirror images, that what we call as a serial molecules, and the properties to show serial molecules are called as a seriality. So if the image and the objects are overlap directly, then it is called as aserial. Most of the aserial molecules are optically inactive. The above test of the molecular seriality can be applied by organic molecules by constructing models, its mirror images by drawing 3-dimensional structures, attempting the superimposable them in our mind. There are other acts, however, that are assigned as in recognizing serial molecules. One such acts in presence of 2 simple molecules. In presence of 2 simple molecules, such as propane 2-ol and butane 2-ol, and their mirror images. Let us see it. First one, propane 2-ol, that is in figure A. Now if you have drawn the image of this one, then you will get it figure B. And if you rotate this figure B, you will up to 180 degrees Celsius, then you can see figure C. B is the mirror image of A in this case, and B is rotated up to 180 degree, then C is obtained. C is superimposable to A. Now, as you can see very clearly, propane 2-ol does not contain any asymmetric carbon, as all the 4 groups attached to the tetrahedral carbon atoms are not different. When rotate the mirror images of the molecules by 180, then the structure C will get and try to overlap with the structure C with structure A. These structures completely overlap. Thus, propane 2-ol is an aserial molecule. Like this, you need to see it whether the substance is aserial or not. Now, let us see again for the butane 2-ols. Now, this is the structure for butane 2-ol in the figure D. Now, this figure D image is on figure E. If you rotate up to 180 degree, then you will get figure F. Butane 2-ol has 4 different groups. 4 different groups attached to the tetrahedral carbons. That means in the middle carbon, these 4 different groups are attached. And as expected is serial. As I already told that if 4 different groups are attached to the one carbon atom, then it is of serial. So some common examples of serial molecules such as 2-chlorobutane, 2,3-dihydroxypropanol, and bromochloroiodomethane, 2-bromopropanoic acid. All these are serial molecules. The stereoisomers related to each other as non-superimposable mirror images are called as enantiomers. So enantiomers are the stereoisomers which are of non-superimposable mirror images to one another. So enantiomer possess identical physical properties, namely melting point, boiling point, refractive index, but they only differ with respect of the rotational plane of the polarized light. If one of the enantiomers is dextrorotatory, then the another should be levorotatory. So here you need to understand the definition of enantiomers, and you should be able to find out the serial molecules. These two parts is important for the final exam of BO. Now, what are the properties which differ in between the two enantiomeric forms? That also we can ask as questions. So for that you need to understand that enantiomers will always possess identical, means same physical properties, but they differ in their optical rotations. The sign of the optical rotation is not necessarily related to the absolute or the actual configuration of the molecules. That also you need to recall it. A mixture containing the enantiomers is in equal proportions will always have zero optical rotation, because both the magnitude should be same, only the symbol should be differ. So plus one minus one is, you assume it, so plus one or minus one, your answer is 0. So always a mixture of two enantiomeric forms which is in equal amount will always have zero optical rotations. Such rotations due to the one isomers will cancel by the rotation of the others isomers. Due to that, they will have zero optical rotations. So such a mixtures which have zero optical rotations are called as a racemic mixtures, and the process of making racemic mixture is called as a racemization. So your example 10.8, you need to see it here. You need to find out serial center. So the first one means the first part of the Roman number 1, that is serial, and here second part of the means the first part of the Roman number 2 question, that is figure 1, that is your serial, and in the third case also the first part is of serial, because it will have 4 different groups on that carbon. Thus carbon become your asymmetric, and hence it is of serial. Now we will see about the retention of configuration is the preservation of the arrangement of the bond to the asymmetric center during the chemical reaction or transformation. That means in a chemical reaction, if the arrangement of the molecules remains same in directions, then it is called as a preservation or retention of the configurations, we can say. So let us see one example. In general, if during reaction no bond of the stereoisomers is broken, the product will have the same general configuration of the group around the stereoisomers as that of the reactants. Such a reaction is said to proceed with the retention of the configurations. Now let us see your levo-2-methylbutane-1-ol plus ICl. If you heat it, you will get it your plus 1-chloro-2-methylbutane. It is important to note that configuration at the asymmetric carbon in the reactant and product is same, but sign of the optical rotation has changed in the product. This is so because two different compounds with the same configuration at asymmetric center may have different optical rotations. One may be dextro and another one may be levo rotatory. Now let us see about the inversion or retention or racemization. There are two outcomes for the reaction at the asymmetric carbon atom when bond directly linked to the asymmetric carbon atom is broken. Now consider the replacement of X by Y in the following reactions. In the first one, we in the figure B. Now figure B is obtained when we added Y to the C, then to this asymmetric carbon atom. Now here if you put, you can get this one, or if you put, you can get this one. Now if you put Y again, then you will get a mixture of A and a B. Means this is figure A and this is figure A and B. You will get it here if you put Y again here. Now if A is the only compound obtained, then the process is called retention. Now in this case, the X direction and Y direction are in the same, others arrangement are same, so it is called as a retention in configuration. Note that configuration has been rotated A. Now if B is only compound obtained, the process is called as a inversion of configurations. In this B, the direction of this X will changes to here. So this, if the direction of arrangement of the molecules is changes, now this is on the left side, but it becomes now this is on the right side, but now it becomes left side. So if the arrangement is changes, then we call it a inversion. If it is same as the reactant, then it is called as a retention. If the direction is changed, then it is called as a inversion. So you need to understand what is inversion, what is retention. And we have already seen that AB, you will get it. That means this AB means that one is in the retention product, another one is in the inversion product. So the mixture of that will shows this optically inactive. That means the optical rotation becomes zero, and because of cancellation of one rotation to another, and such a mixtures which have zero optical rotations, what we call as a racemization. So what we mean by racemization is, we have already know, alloys racemic mixtures become optically inactive. This also you need to understand it. In case of optically active alkyl halide, the product formed as a result of SN2 mechanism has the inverted configuration as compared to the reactant. This is because the nucleophile attack itself on the side opposite to one where halogen atom is present. When minus means that LiBo 2 bromo octane is allowed to react with the sodium hydroxide, then you will get it plus means that dextro octane 2 ol is formed with the OS group occupying the position of the opposite to what the bromide has occupied. So this is the figure. Now thus in SN2 reaction of optically active halides are accompanied by inversion of configuration. So we can ask, if optically active alkyl halides undergo SN2 mechanism, what type of product will be formed? So your answer is inversion of configuration will be formed. That means the direction of the motion will be changes here. Always you must recall this one. Now in case of optically active alkyl halide, if it undergo SN1 mechanism. First one we have discussed about the SN2 mechanism. In SN2 mechanism, it gives inversion of the product. Now, if it is of SN1 mechanism, then SN1 reactions are accompanied by the racemization. So, you will get a raceme mixture. That means optically active alkyl halide under SN1 mechanism, you will give a raceme mixture. Your optically active alkyl halide under SN2 mechanism, then you will get inversion in figures. So you must recall this one. And why it will perform racemization or raceme mixture? Let us see it. Actually, this is the answer part. You can see it. Actually, carbocation form in the slow step being sp2 hybridizes, and which is planar. That is means a serial in. So the attack of nucleophile may be accomplished from either side of the planes of the carbocation, resulting a mixture of the products. So because of this, you will get a mixture. That means plus and minus. So you will get 0 optical rotations. Now let us see about the elimination reactions. As we have already know that elimination means removal of one of the components from the reactant, we call as a elimination reaction. Elimination reactions are of 3 types. One which we call as a alpha elimination reaction, another one beta elimination reaction, another one gamma elimination reaction. Here you need to understand what is alpha, beta, gamma carbons. Alpha carbon means those carbon where the functional group is attached, that we call as alpha carbon, and next to that where the functional group is attached, that is what we call as a beta carbons. So beta carbons are those carbons adjacent to the alpha carbon, you can say, and next to that means that adjacent to beta, that we call as a gamma. If the outgoing groups are both from the alpha carbon, then it is called as a alpha elimination reaction. If the outgoing groups are one from alpha and one from beta, then it is called as a beta elimination reaction. If the outgoing groups are one from alpha and one from gamma, then it is called as a gamma elimination reactions. This is a basic. Now, when haloalkanes with beta hydrogen atom means those hydrogen atom which is attached to the beta carbon atom, that we call as a beta hydrogen atom. So haloalkanes with beta hydrogen atoms is heated with alcoholic solution of potassium hydroxide. Then elimination of hydrogen atom from the beta carbon and halogen atom from the alpha carbons occurs. So that means we have one halogen atom will be removed from the alpha and one hydrogen atom will be removed from the beta. So you will get an alkene. So this is the example which we have seen here. This is alpha, this is beta. So from beta, hydrogen will be removed. So hydrogen removed means the electron pair will be given here. So it becomes double bond, and the excess electron which is in this alpha carbon will be taken by X. So you will get a double bond compounds. Now, in the previous example, we have already know that the alkene is formed due to the removal of 2 components. One is from alpha and one is from beta. So it is a beta elimination reaction. So always halol can undergo beta elimination reaction. This is what you need to recall in your mind. Now, based on this one, if there is more than one hydrogen atom, that means beta hydrogen atom, then there is a possibility to form more than one products. So for that, which product will be getting as a major product, that will follow by a rule called as a Sajjeb rules. Now let us see what is Sajjeb rules. Now according to Sajjeb rules, in dehydrohalogenation reaction, the preferred product is that alkenes which has greater number of alkyl group attached to the doubly bonded carbon atoms. So we'll get the products in which the means that we'll get the alkenes in which has greater number of alkyl group attached to the double bond. So now let us see one example. 2-bromopentane. This is the reactants which we have taken. On that, let us add a nucleophile, that is OH is added to that. Then we will get a beta elimination reactions. Now we will get an alkene. So what type of alkene we will get? One is there in the first part, that is your pen-2-ene. Pen-2-ene. That means here this hydrogen will goes and this hydrogen will give electron pair here. So your bromine will take electron there. So you will get CH2, means that this product you will get it. But this product you will get is 19%. And again another is there. In the another, here we can remove this one, and one hydrogen we can here one hydrogen you can remove here, and another hydrogen you can remove, another Br you can remove here, so that you will get it this product. Because here you have beta hydrogen, you have beta hydrogen here, so you can remove one from here or you can remove one from here. If you remove one from this part, means on carbon number 1, then you will get pen-1-ene. If you remove one hydrogen from here, you will get pen-2-ene. So in case of pen-2-ene, double bond, here carbon number 2 carbon is here, here near the double bond only 1 carbon is there. So this one will have more product according to Sajjev's rules, and this is important for the exams also. Good morning. Today we will see again a reaction with metal. Most organic chlorides, bromides, iodides react with certain metals to give a compound called carbon metal containing carbon metal bond. Such compounds are called as organometallic compounds. It is an important class of organometallic compound discovered by Victor Grignard in the year 1900s, and that is alkyl magnesium halides, which was represented by RMgX. So this RMgX is also called as Grignard's reagent. These reagents are obtained by the reaction of haloalkanes with magnesium metal in dry ether. So CH3, CH2, Br ethyl bromide plus magnesium in presence of dry ether, you will get it ethyl magnesium bromide. So ethyl magnesium bromide is of one of the Grignard's reagent, which is one of the important organometallic compounds in the organic chemistry. Now we'll see the uses of Grignard's reagent. Or before that, let us see it how Grignard's reagent will have. In the Grignard's reagent, the carbon magnesium bond is covalent but highly polar, because the electronegativity of this halide is more than the electronegativity of alkyl group, and so the electron pair between the Mg and X will be taken by this X. So X become negative, slightly negative, and magnesium metal become slightly positive. So again we have here this alkyl group also can behave as an electropositive groups, or as alkyl group can donate electrons to this magnesium. So you can say it is apolar. So if it is apolar, then it will shows ionic character. Grignard's reagents are highly reactive and react with any source of the protons to give hydrocarbons. Even in water, alcohol amines are sufficiently acidic to convert to the corresponding hydrocarbon. So if you react with this, that means Grignard's reagent with water, you will get your alkanes with magnesium hydroxyhalides. It is therefore necessary to avoid even traces of moisture from the Grignard's reagent. This is why a reaction is carried out in dry ether. So we can ask the reaction of Grignard's reagent. In the preparation of Grignard's reagent, your alkyl halide is react with magnesium in presence of dry ether. Why? So your answer is even in presence of moisture, Grignard's reagent can combine to give the corresponding alkanes. So you will not get Grignard's reagent in the preparation. That is why we need to remove water. So in order to remove water, we use the reaction in dry ether case. So this is the reason for that. Now let us see about the Ward's reaction. Ward's reaction. Ward's reaction means alkyl halide react with sodium in dry ether to give hydrocarbon containing double number of the carbon atom present in the halides. Then these reactions are called as a Ward's reaction. Suppose 2 times of Rx plus 2 times of Na in presence of dry ether. Then you will get Rr plus 2NaX. Here in the first reactant is only 1 R, although it have taken as 2 molecules, but it is of only 1 R. That means you will methyl chloride. Say if you have taken 2 molecules of methyl chloride along with 2 sodium in presence of dry ether, then you will get it ethane. So one is methane, now comes to ethane, like this one. So this reaction is called as a Ward's reaction. Now nucleophilic substitution reaction. So alkyl halides means that here aryl halides are exactly less reactive towards nucleophilic substitution reactions. Give reason. This question is more than 3 times in the board exam. So you have 5 reasons. Out of that, resonance effect is one of the important reasons. So in haloarenes, the electron pair on halogen atom are in conjugation with pi electron of the ring, and thereby it will show resonance structure. That means here this lone pair will gives to here, then you will get a double bond, and here this valency is more, so this electron pair will gives to here, so it will get a negative charge here. So that means the delocalization of pi electrons here due to the rotation of these pi electrons. Like this one, delocalization of pi electrons take place. This structure is called as a resonance structure. The C-shell bonds acquire a partial double bond characters due to the resonance. As a result, bond cleavage in haloarenes is difficult than haloalkanes, and therefore they are less reactive towards nucleophilic substitution reaction. So by using this one, we can ask aryl halide are less reactive in nucleophilic substitution reaction as compared to the alkyl halide. Give reason. So first reason is your resonance structure. In case of alkyl halide, it does not have, it is of single bond, so which make easier to break. Whereas in case of aryl halide, it is of double bond, partial double bond. Due to double bond, the breaking of this bond is difficult as compared to the your single bond. This is what it was there. Second reason is that difference in hybridization of carbon atom in CX bond. In case of haloalkanes, it is of sp3 hybridized, whereas in case of this, in case of aryl halides, it is of sp2 hybridization. So sp2 hybridization means that the carbon with a greater S character and greater S character is more electronegative, and that can hold the electron pair of CX bond more tightly than sp3 hybridized carbon atom in case of haloalkane. as sp derivation will have less s character. Thus, the CCl bond length in haloalkane is of 177 picometer, whereas the haloarenes is of 169 picometer. Since it is difficult to break the shorter bond than the longer bond, therefore haloarenes have less reactive towards the nucleophilic substitution reaction. Third reason for this is the instability of the phenyl cations. So if you remove arenes, then you will get, if you remove halogen from aryl halide, then you will get a phenyl cation. Phenyl cations thus form as a result of self-ionization will not be stable by resonance. Therefore, S1 mechanism is not possible. This is what it was there. So another case is that because of the possible repulsion, it is less likely for the electron-rich nucleophile to approach the electron-rich arenes. Now let us see some reactions of haloarenes. Replacement by hydroxyl group. This is the first one. So we can ask, how will you convert chlorobenzene to phenol? Then you should write this first reaction. First reaction, chlorobenzene is heated with sodium hydroxide at 623 Kelvin and 300 atm. Then you will get it phenol. And this question was already in the board exam. How will you convert chlorobenzene to phenol? Another one is the presence of electron withdrawing group at ortho and para position increase the reactivity of haloarene, whereas the presence of electron releasing group like alkyl group that decrease the reactivity of haloarenes. This point is also important. Here we have nitro group in the para position, so it may increase the reactivity of haloarenes than chlorobenzene. So like this one we can ask, compare the reactivity of the following. One we can give it this chlorobenzene, another one we can give it like this one. So if number is, you must recall that if electron withdrawing groups is present at ortho and para position, it increase the reactivity. So when we compare this to this one, we will have more reactive than this. You must recall that. And instead of this, if it is R, then that containing R will have less than this. So like this one. So your main idea is the presence of electron withdrawing group at ortho and para position increase the reactivity, whereas presence of electron donating group like alkyl groups that decrease the reactivity of haloarenes. Here in the second again we have two electron withdrawing groups, so it will have faster than this. So like this one, it is there. Now in this we have three electron removing groups, so slightly when you warm you will get this trinitrophenol, you will get it. So this is what we have seen here. So this part also we can ask, para-chlorobenzene, how will you convert para-chlorobenzene to 2,4,6 trinitrophenol. Like this one we can ask. So, but there is no effect if the nitro group is present at meta position. So this is what you need to calculate. And your question which is here, and the actual question, can you think why NO2 group shows its effect only on ortho and the para position but not meta position? This question you read yourself. This is also in the board examination. Now we will see electrophilic substitution reaction. Haloalkane undergo the usual electrophilic reaction of the benzene ring, such as halogenation, nitration, sulfonation, Federal-Kraft reaction. Halogen atom besides being slightly deactivating at ortho and para directing. Therefore, further substitutions occurs at ortho and para position with respect to the halogen atom. The ortho para directing influence of halogen atom can be easily understood. So, by seeing this resonance, so we can ask this part also is why halogens are the ortho-para directing species in haloarenes. So first one is resonance itself is there. So ortho and para will have more electronegatives. So electrophilic particles will be easily attached here. In case of meta, electron density is less, thereby the attack of electrophile in the para is easier, in the ortho is easier, but least means that very difficult in case of electron-least meta position. That is why these halogens are of ortho-para directing groups. Now, first one, halogenation, let us discuss it. Halogenation means addition of halogen that we call as a halogenation reaction. So your chlorobenzene plus chlorine in presence of anhydrous ferric chloride, then you will get 1,4-dichlorobenzene as a major product and 1,2-dichlorobenzene as a minor product. Why para is a major product? Because in para electrical distribution is more, so electrophilic attack is easy in case of this high electronegative area, that is para position. So para products are more here. Same thing like this in the nitration also. Nitration means this chlorobenzene combined with fuming nitric acid. The mixture of ice NO3 with H2SO4 is called as a fuming nitric acid. So if you mix chlorobenzene with fuming nitric acid, then we get it 1-chloro-2-nitrobenzene as a minor product and 1-chloro-4-nitrobenzene as a major product. Like this one, addition of sulfonoid ion. Sulfonoid ion means ice-O3 ice, that we call as a sulfonoid ions. So for sulfonation, you need to add that sulfuric acid and heat. So if you added chlorobenzene with sulfuric acid and heated, then you will get it 2-chlorobenzene sulfonic acid as a minor product and 4-chlorobenzene sulfonic acid as a major product. So this is what about the nitration, chlorination and sulfonation. Now we'll see about the Federal-Kraft reaction. So these Federal-Kraft reactions are of two types. One is Federal-Kraft acylation, another one is Federal-Kraft alkylation reactions. So what do you mean by Federal-Kraft acylation? What do you mean by Federal-Kraft alkylation? You must recall it. So here, addition of an alkyl group, that we call as a addition of an alkyl group in presence of this aluminum chloride, that we call as a Federal-Kraft alkylation reaction. Addition of acyl group to the haloarenes in presence of aluminum chloride, we call as a Federal-Kraft acylation reactions. So chlorobenzene when combined with methyl chloride in presence of aluminum chloride, then you will get it 1-chloro-2-methylbenzene as a minor product and 1-chloro-4-methylbenzene as a major product. Here CH3 group is attached to the chlorobenzene, so it is of Federal-Kraft alkylation reactions. Now chlorobenzene combined with acetyl chloride in presence of aluminum chloride, then you will get it 2-chloroacetophenone and as a minor product and 4-chloroacetophenol as a major product. So here an acyl group, that is CH3CO, is added to your chlorobenzene. That is why it is called as a acylation reaction. So this H3CO Cl we call as acyl chloride. So this is what we have, and this question was already there. I have already told the answer also. Chlorine is an electron withdrawing group, yet ortho and para directing in the electrophilic substitution reactions. Why? This was already explained. I have already told that in the ortho and para position, it will help your electron density more due to the resonance, and this resonance help them to attack an electrophile chlorine easily in ortho and the para position. That is why they are of ortho-para directing species. Now we'll go to this reaction with metal. Reaction with metal. So first one, Warsh-Fittig reaction. A mixture of an alkyl halide and aryl halide gives an alkyl arene when treated with sodium in dry ether. Then we'll call it as a Warsh-Fittig reaction. Here alkyl halide means that Rx, and aryl halide means that benzene ring with X. Then if you heat it with sodium in presence of dry ether, then alkyl means R is in the benzene ring, so alkyl arenes we get it. So this preparation is first done by Warsh and Fittigs, so it is called as a Warsh-Fittig reaction. Another one is Fittig reactions. Fittig reaction means aryl halide also give analogous compound when treated with sodium in dry ether, in which two aryl groups are joined together. That means in Fittig reaction, two molecules of aryl halides, you take it and heat it with sodium in presence of dry ether, then both the two aryl groups are joined to get diphenyl and sodium. So this reaction is also important. So Warsh reaction and Warsh-Fittig reaction is important for the exams, and this 10.8 and 10.9 in your textbooks was already in the board exam. You try to solve it, and remaining part of, that is polyhalogenic compounds, was deleted for this year, so you need to read the remaining part. This is the end of this chapter. Thank you.